Okay, so in this video, right, so welcome back to Unit 3 for AP Physics C, the Work, Energy, and Power unit. In the last video, we talked about constant force. Now let's look what happens when that force varies. Okay, so this is going to be different than what AP Physics 1 does because now we're going to look at what happens when we vary that force, okay, and that's going to introduce in calculus. So really, again, physics C, real world. So what happens is many forces that in the real world are not constant, right? So they're going to vary with your force in your direction. So what does that mean? The work done by a variable force is going to be the area on an F cosine theta versus D curve, or in this diagram, you can see it's an L curve, okay? So with that, anytime we talk about area, right, we talk about the integral. So work is the integral from x initial to x of F cosine, or let me write it more in kind of the calculus way. All right, so it's going to be F dot dx. Okay, again, these are going to be vectors, right? And so when you have that dot product, again, that's why you have this F cosine theta running around, okay? But you can see it's the integral from your initial x position to your final x position of F dot dx. Now, one of the most common variable forces or varying forces that we will encounter is the spring force, okay? And so it's going to be F equals kx, right? So that's going to be the equation for the spring force. Sometimes you see a negative sign here because it is a restoring force, okay? But so what happens is when you stretch a spring, right, the force, the stretch that spring is varying. So that the same stretching and compressing distance does not produce the same work done on the spring. So if we want to just do that kind of conceptually, so the work done on a spring, okay, it's going to be the integral of F dot dx, and we'll call this like F, from 0 to x, okay? Because we're going to go from its relaxed state to just some position out there, okay? And so I'm going to say it's the integral from 0 to x of kx dx, right? So when you do this, so you substitute in what your what the function for your force is, and now you take the integral of that, okay? So the work done by a spring is 1/2 k x squared evaluated from 0 to x. And so that's going to be 1/2 kx squared. Okay. Now, you do have to be careful because we evaluated this particular integral from 0 to x. You need to plug in the numbers there, right? So if it's not 0 to x, you need to make sure you plug in your limits, right? Because I guarantee you that if you did from 0 to 4 and 4 to 8, even though they're the same, 4 meters, I don't know why you would stretch a spring 4 meters, but even though they would still be technically a displacement of 4 meters, that the work done is going to be much different, okay? So let's look at an example. So we have a force exerted by a spring. It's given, now note the equation, it's 1/2 kx to the fourth. So if k is 100, find the work done on a spring or on a mass from a equals x equals 0 meters to 2 centimeters and then 2 to 4 centimeters, okay? And so, so part A, right? So we're going to say the work is equal to the integral from 0. Now you do have to be careful because we want this in meters. So 2 centimeters is 0.02 meters, right? 4 centimeters is 0.04 meters, okay? So I'm going to go from 0 to 0.02 of 1/2 kx to the fourth dx. But they do give us that k is 100. So I got 1/2 times 100 of x to the fourth dx. And we're going to go from 0 to 0.02. Okay, so this is 50. But remember, I can pull that outside of my integral because it's a constant. Right, and so x to the fourth is the integral of x to the fourth is 1/5 to the fifth, 1/5 x to the fifth. So it's 50 times 1/5 x to the fifth from 0 to 0.02. Okay, so now here's where you get a little, you can do different things, right? So it's going to be 1/2 50 times 1/2 x to the, 0.02 to the fifth minus 1/5 0 to the fifth. Okay, and so all of our and then the whole thing's going to be multiplied by 50. And so I'm running out of room. So the work done by the spring in this case would be 9.92 times 10 to the negative 7th joules, or Newton meters. Okay. Now let's look at what happens. I apologize. I wrote down the wrong answer. I was looking at the wrong part of the notes. So this is not going to be 9.92. This is going to be 3.2 times 10 to the negative 8th joules. Okay. And so now we go over to the other side. What happens when it goes from 2 to 4 centimeters? Note it's the same displacement of 2 centimeters, but watch what happens. So I still have essentially my calculus is going to be the same. Okay, so I'm just going to substitute in now the 0.04. So work equals 50 times 1/5 0.04 to the fifth minus 1/5 0.02 to the fifth. Okay, and all that's going to be multiplied by 50. And so my work done, going essentially the same displacement, you're going to see it's going to be much less. Okay, it's going to be 9.92 times 10 to the negative 7th joules. So as you can see, as it gets stretched out, the spring is actually easier to move from, to easily displace it. Okay, so all of our, if you want to say all of our math work was done on this side, we just used that same equation, right, to do our part B. That's why part B seemed to be much easier. Okay. All right, so that's work done by varying force. Next thing, we're going to now make this relationship back to kinetic energy, a topic that you guys have probably been working with since middle school, or if you took AP